Today.
It's uploaded.
Okay.
It's uploaded.
Alright. Did you show me?
And I think it's,
What do you say?
Cool. I'm
Recorded.
gonna, get the glue stick.
You're
I first trim it.
Do that.
Oh, okay, you tell us that.
This stuff
10
where
minutes and 20 minutes.
anytime we have difficulties. So,
There they are.
Okay.
hello there. How's the microphone today?
Okay. Let me see, it's all right? It's okay.
It's okay?
Yeah.
Okay, then I suppose we should start.
Yeah, you can start.
What's up, James?
So,
Did you have a good weekend?
let's start. So we'll start where we left off last time. We were still finishing up data pre-processing. So, but before we begin, any questions again? Questions in Daytona Beach? No? Yes?
And we got a great success for the Umadoption project.
Oh, nice.
And we get the astronauts really interested in post our offering Twitter and Facebook. Actually, thousands of people are following. I don't know they cut off now. Okay.
Oh, that's great.
Yeah, the second one, the third one, the comes.
What do you say?
Go Team Eco Dolphin.
Yeah, they know it. The kids and learn and all see it, but now it's running great.
Oh, Eric.
Okay, great. So, any questions here about what we talked about on Friday here? Katie? Okay. So I'll bring up where we left off on, so we were, okay, so we're going to start with where we left off with data pre-processing, and I'm trying to remember exactly where that was. We went over sampling, data reduction. Maybe we got through quite a bit, I suspect. I think we covered data preparation, mathematical computation.
Yeah, we do.
Okay. So we're going to start off with one of the topics that really we actually have to start knowing. So if we're going to be clustering or classifying, we need to have some sort of a measure of distance, a measure of similarity. Because we don't know what kinds of things we're going to be working with. If we're looking at words, how do you measure similarity between two words, between vectors? So there's a number of different measures. So let me make this full screen. So some standard measures, and we'll cover these in more detail as the class comes on and as we need them. Euclidean distance, everyone should be familiar with Euclidean distance. And I don't just mean on a plane, but in 3, 4, 5, 10, 100 dimensions. okay? The sum of the squares of your different directions, and then the square root. Direction cosines. So that's another measure in terms of the angles, basically, you're looking at between different objects. So we can measure the direction cosines, again, in different directions. Some other ones, simple matching and Jaccard coefficients. So now you're looking, so for example, you could look at binary strings, how many and how many ones match, how many zeros match versus how many mismatches. Set similarity. So this actually is, I find, a very useful measure, and I should probably, let's see, go to the whiteboard here. So here, set similarity. Anybody seen that measure before? Say you have two different sets, A and B, right? So I will draw, let's see. If you think of two sets, let's draw the Venn diagram. And set A and set B. So here's set A. Right? So in terms of the set similarity measure, also called the Tamamoto measure, what you're going to be looking at is, in terms of similarity, a good measure would be if you have a whole bunch of objects in A and B. So it would be the number of A intersect B all over the number in the union.
And this is a similarity.
That's a similarity measure. So basically what you're measuring is, if you look at the union here, so you're looking at the entirety of A and B. So that's, if you think about this in terms of, that's your unit, that becomes your set of words. Maybe you're looking at the similarity between cat and dog, right? So A could represent cat, B in that case could represent dog. What properties, how many elements are, I mean, we're not going to see the cats and dog, somebody being in both, right? But maybe you're looking at properties of cats and dogs. So now it would be properties of a cat, properties of a cat, dog. They both have 4 legs. They have a mouth,
One eye.
a nose, a tail. So you might, if in that case, you might be looking at properties or attributes rather than the actual instances. Whereas in other cases, you might be looking at instances and you want to know how often is there overlap between the two versus between the totality of the two. So if you think about it, set similarity, that makes sense that you could use a measure like that to measure the similarity between two objects.
Like the particles are a whole.
Right, exactly. So now I want to So go back to the slide. We were in. I don't remember, where did we end up? Yep, right there.
Cool. Sweet.
So that's the Tamamoto distance. Hamming distance, you might, computer scientists, you might have seen the Hamming distance before.
Never heard of it.
Never, you might have heard it maybe under a different name. It's the number of differences between your ones and zeros, or numbers of, so if you have 1, 1, 0, 1, and 0, 1, 0, 1, they're 1 unit away, right? Because you've got one difference there. So it's, in a lot of ways, it's, yeah, that's.
That's it.
Edit distance, you might have heard of edit distance. Anybody? It's how many insertions, deletions, and changes. The minimum number, if you have, again, 2 strings, and they could be binary or they could be word strings, how many insertions, deletions, and changes you have to make at a minimum. So it's going to be the smallest number of those changes, the edits that you need to make to change one string into another string. And other measures of similarity and distance are probability-based measures. And for the life of me, that one, the last one, I'm forgetting off the top of my head. That's also, that uses a covariance matrix. It's going to be a generalization of Euclidean distance, and we're going to talk about the covariance matrix today in another context. So basically, what it is you take a vector of your difference between 2 vectors, and both as a row and as a column. And you're going to, in the middle, you'll give this covariance matrix that I'll introduce at the end. And that has a special name, it's called the Mahalanobis distance. So the key thing here is there's a lot of different measures of similarity, depending, again, on the context of the problem. So how do you know when to choose a different similarity measure? It's like everything else that I've been trying to really emphasize early on here with the data. Everything's going to be problem-specific and data-dependent. What type of data do you have? Is it binary? Is it strings? Is it vectors? Continuous data? It's going to depend on the domain knowledge underlying the problem that you have. The purpose. And a lot of measures, not all of the measures, have metric properties. So maybe those are going to be of interest. Maybe you want something that satisfies a standard, what's called in mathematics a metric. Some of you might have heard of metrics before. These are going to be relations that satisfy the standard distance properties, that the distance between 2 objects is always non-negative. Symmetry, the distance between object A and object B is the same as the distance from B and A. Now, not all your distances are going to always satisfy these. And the third one is the standard triangle inequality. the distance from A to C is never going to be less than the distance from A to B plus the distance from B to C. So if your distance satisfies those three properties, then it's called a metric. And I think that's, we've moved on. Cool. Booyah. So we're now moving on into data exploration and data visualization. And so we're going to start off relatively simply with one variable statistical explorations of our data, right? A lot of these may be should be fairly familiar. So you can start making tables of your data, how frequently it occurs and what percentiles. Basically, those are going to be measuring the same thing. We can summarize data using our standard statistical measures, mean or median, mode. That measures the center of the data. And then you can also measure the spread of the data. This should be fairly familiar to everyone. Standard measures of spread are the range, standard deviation. A couple others I want to mention here. These last three are less sensitive to outliers. So if you have an outlier data, the standard deviation can be thrown off a little bit more. So we can also talk about the absolute average deviation. So let me, AAD, the median absolute deviation in the interquartile range. So let me, let's see, where's the eraser?
What's that little X do?
Yes. Okay, so the AAD, so basically, that's the absolute average deviation. So if you remember how standard deviation, it's going to be 1, I'll type it in here, equals 1 over, if you have, say, m data points, it's going to be 1 over m. And now instead of putting the square root of the squares, it's actually going to be, I'll type in sum of, over, say, from I equals 1 to m, sum of the absolute values of the x sub I minus x bar. Is that fairly clear, or should I write it in mathematical notation?
Are you good, Vinny?
So you're, instead of taking the square root of the squares, now you're using absolute values. And you're just finding the average, or the average of the sum.
Okay.
Okay. And the, let's see, the next one
Was MAD?
was MAD, and that stood for the median. So that measure, so I'll start a new text box here. So MAD, and that's going to be the median of the absolute values of x1 all basically x bar x2 minus x bar. So basically you're gonna list all your values minus your average. And then you're going to take the median of all of those values. Does that make some sense? Pretty straightforward. So you notice on the AAD, you're actually taking the average of the difference between your values and the mean. And on the second one, you're taking the median. Top one, you're taking the median, the second one, you're taking the mean. And the last one is the interquartile range, or IQR. And that uses percentiles, so that's going to be your 75th percentile value of your data. So interquartile, so it's going to be the minus your 25th percentile. So you're taking the middle 50% there. You get your 75th percentile value and your 25th percentile value. Those are just a couple of other measures that one can use. Okay, so going forward, now, this data mining, we're not just looking at single variable statistics. So we typically have a lot of attributes. So we're going to be, another approach is to start looking at multivariable statistics. So what do we mean here? Say you've got 10 different characteristics, 10 different attributes, and we want to try to find your mean. So how do you do that? How do you find the average? That's pretty straightforward. Any inputs here?
You average each one individually?
Yeah, right, so it's going to be, say you've got 10 different dimensions, and you want the center of all of those, right? And that's going to be found by taking the average of your first dimension for your first component, for your first dimension. Your second dimension will also be the average in the second dimension values. Okay? Pretty straightforward. Should I write it down on the whiteboard?
How do you, well, okay, so you have 10 different attributes, how you gotta figure out how they're similar to each other, or?
Well,
you
the
just take
similarity
averages?
measure is what you're going to be using to measure,
Okay.
right? And to find an average of some sort. Now now you've got all these values, we're not talking similarities here, we're just trying to find the center of a group of different data points. Now the data might be 2 dimensions, right? So in order to find the center, think of calculus, where you find the center of mass. It's it's not just a one-dimensional rod, it might be in 2 dimensions, and so you have an X bar and a Y bar. Right? Is that?
Sure, yeah.
Now extend that to 10, 20, 100 dimensions.
Okay.
So I mentioned that we'd be coming back to the covariance matrix. So I'll go over that, what we mean by covariance here. So okay. So let's refresh our memory, before we move on, let's refresh our memory about variance, which was the measure for standard deviation, right? Any feedback here? Eric?
Variance, standard deviation, yeah, I don't like that stuff.
Isn't that the standard
Oh.
deviation square?
The variance is the standard deviation squared. So the variance of a single variable, right? So I'll,
No,
Probably either public or consumer.
so the variance of a single variable x,
What is your number?
so we already know this. So if we're looking at it, and it depends on whether we're looking, I mean, there's a technical little glitch depending on whether we're looking at a sample or a population. And typically we're looking at samples. So it's gonna be 1 over the number of data points minus 1. Yes?
Can you make the font a little bit bigger? My eyes are really struggling right now.
Oh, fine, I thought it was just medium.
Yes, I can.
Cool. Trying to use my
Nice.
good eye,
Yes, yes, that's.
Is that better? Should I make it even larger?
That's good,
That's
you're-
fine.
but that's perfect, thank you.
Okay, good question. Okay, so then how do we calculate this? Again, I'm gonna just use math here, or English letters here. The sum of over all the I values, my x minus I values minus my mean squared. So I'm gonna square all the values, subtract the mean from all the data values I have, square those, add those all together, 1 over the number of data points minus 1. And the variance, we already mentioned, measures how the dispersion of the data, how spread out the data is in one dimension, right? So now we can do the same thing, but the question is, now we want some way of measuring what's called covariance. And it's going to be a related concept called correlation, which is ultimately where we're trying to go with this. So covariance is almost the same idea here. I'm going to just give it for, say, x and y, because then it generalizes to more than 2 dimensions. But you might be interested, how are my variables x and y related, if they are? Covariance, it's an imperfect measure, but if we notice in this formula here, we're subtracting the xi minus the x bar and multiplying it by itself. And so we're going to now measure the covariance between 2 variables. Between, say, x and y. Again, it's going to be very similar. It's going to be 1 over the number of data points and minus 1 for a sample. And again, we're going to have the sum. But inside here, we're now going to look at, and here I'm just doing it for 2 variables, and we'd have to change some notation to try to include more. But basically I'm going to take my xi minus my x bar, times my yi minus y bar. So you should be able to see, by looking at these 2 formulas, the similarity. Instead of xi minus x bar times itself, I'm now multiplying by my other variable.
What happens if that ends up being negative?
Okay, good question. It's fine. It can be positive, it can be negative. So what the covariance roughly is going to measure when we get to correlation, which is the similar concept here, although it's actually it's going to be in essence, normalized to be a value between -1 and 1. If the covariance is positive, what that indicates, and as I say, it's not perfect. And I want to emphasize that because there's this concept of independence. If x and y are independent, then the covariance is 0, but covariance 0 does not mean that they're independent. So it's a one-way statement. But basically, if the covariance is positive, that indicates that as x increases, then so does y. Whereas if it's negative, it's a negative correlation that way.
Right, so x increases, y decreases?
Right. So moving on, we'll get to correlation here. They use R, but it's often X. So now a row, I'll just use R. So again, here I'm just subscript XY, meaning between my X variable and my Y variable. And in general, you might have 20, so maybe you're going to subscript it X of K, X of L, something like that. But basically, we're going to now take the covariance between the two variables and divide by this sample the standard deviation of the x variable and the standard deviation of the y variable. Okay? And now what that does, that gives now a value always between -1 and 1. So if you had an R value here of 1, that would relate to a perfect correlation between, positive correlation between x and y. An R value of -1 corresponds to a perfect negative correlation. So as R increases, Y decreases in the same manner. Now, so correlation, it's called the correlation coefficient. So this is your correlation between X and Y. Again, it's not perfect. It's basically, if you're close to 1, and close depends on how much data you've actually accumulated. The more data you've accumulated, the less close it really needs to be to 1. But you can say that there seems to be some sort of dependence or correlation between the two variables. Values near 0, it's like totally random. Okay. So where did we leave off?
The ones,
We're just on the first one?
no.
So we can then create a matrix, right? Because you're going to have, so your variances will be the covariance of x and x, right? xi, x1 and x1, x2 and x2, because it's, if you look at if you remember how it was defined, basically you've got your ith row, jth column in general. And so now you have a covariance between your ith component and your jth component. And that forms then your covariance matrix, and you can similarly form a correlation matrix by dividing by the standard deviations. So we're gonna move on, kind of one of the key concepts that we wanted to start talking about, and hopefully we'll get to, I wanted to get to WECA at the end of today. That may or may not happen. So I just want to mention two things here. That the order or arrangement of your variables can have an impact in how you see your information. If you swap the orders, things that may have not been obvious may become obvious. I can go through an example of that. And the other thing,
Anytime you reduce rows and you swap the rows and you
swap the rows, oh wait, everything's lining up the way I want it to. You swap the rows, you swap the columns, maybe you have it in a matrix, and at first it looks not that patterned, but if you swap the rows or swap the columns or both, you might be able to start seeing patterns. The other thing there is selection. So that can be useful in visualization, and if we get to WEC, I'll show how that can work. Maybe you don't want to see all your attributes at once. So one of the things that I find is sometimes helpful is you're just going to look at the relationship between two variables at a time. Maybe that helps, maybe it doesn't. Maybe you need more variables in order to start seeing patterns. I don't know how much I want to go through all of these tools. These are different techniques for visualizing data. I don't know if anyone's seen stem and leaf plots.
I have.
A couple of people. Histograms.
Yeah.
Histograms are kind of very similar to bar charts. Just more frequent values. Two variable histograms. So now you can have three-dimensional graphs of, I can draw some of these, Kyle.
I've never seen.
Any of these?
How would you make a three-dimensional histogram?
Okay. So,
That's a good question.
we'll clear this. So you might have, let's see if I can,
Boxes.
yes, I'm looking, I saw that.
Just go to box.
But I want a rotated box, so that's actually not gonna work.
Just do a box inside, like, kind of make your own box.
I
So do
can
that as
do
the
that.
front face and then do.
Let me,
I should
actually,
just share the desktop and find an image online.
could, or I could do this.
Okay.
It's gonna be interesting.
Line. Right, so here could be a two-dimensional, I'm gonna draw a two-dimensional histogram. Okay, so here I could have, say, my x coordinates going along this way, and my y coordinates going along this way, and then, now do they have three-dimensional boxes? They don't.
How do you make one?
I'm going to do is my frequencies vertically, so that might be Z. And so now we might have, some of these values for this particular value of X here. We might have a certain frequency. Those are all vertical lines. Right? Whereas over here, maybe you now have more frequent values for these particular values of X and Y.
Wow, that's a lot better. Oh,
I give it a B+.
Well, except that it didn't take it any higher. So now maybe it goes up here, right? And you're gonna have a cube, in other words, it's gonna be a three-dimensional representation. Does that make sense? So you've got more values as your x and y both increase, and then you can have some, maybe you have even more over here. But you're basically gonna get a grid like that. Mouse is a,
friend.
does that make it clearer, Kyle?
Yeah, absolutely.
Okay.
No.
It looks pretty good, actually.
Well, I didn't finish it, but. Yes, Eric?
That looks good. You're a great artist.
Okay, what else did I not cover? Okay, there's the last one. Okay. So that's, but you've seen histograms?
Yeah.
It's like a bar chart, basically.
I don't know what a stem and leaf plot is.
Stem and leaf plot. It's similar to a,
Tree.
Oh, is that like the trees we were doing?
well, I mean, you can use it for a histogram. So suppose we got some data, okay? So, I didn't want that. Suppose we have a bunch of data. 23.4. 23.4. 23.9. 24.2 or 3. 25.1. I think, is that enough to start with? Okay, so notice, and if we had a whole bunch, what we could do here is we're gonna have stems and leaves. And the idea here is on a stem and leaf diagram is you're gonna start with your stem. And if you notice, all of these start with a 2, and we could do this in a number of different ways. And actually, I'm gonna do it as a, so we could do, say, 2. We could have a number of stems. We could have 23 be a stem. We could have 24 be a stem, and we can have 25 be a stem.
Okay.
And then on each of those, I'm gonna have a bar separating the values. And now it ends up kind of being like a histogram, except now I'm gonna actually put the values here that are after the decimal. So a 4 happens twice, and a 9 happens once. At 24, we have 24.3, and at 25, we have 25.1.
I kind of like that.
So it gives a little bit more information than an actual histogram would, because you actually get the full values, but it also gives you a visual representation as well. Okay. Back to slide. Box plots, this is kind of standard statistical stuff. I don't know if people have seen box plots before.
Probably have.
Yeah.
Well, so this is just another way to represent data, so we'll clear that again. So a box plot, we're gonna first draw a box. And I'm gonna talk about what all this information, sometimes also called a box and whisker plot. So it's gonna look something like this. So, and the idea here is it's going to capture different parts of your data set. So this is still one-dimensional. But basically the middle line here represents your median of all your data, your 50th percentile goes right there. Your minimum value is at this point, and your maximum value is on the right-hand side. And then this point here would be, say, your 25th percentile point. And this would be your 75th percentile. So it gives a visual representation of a lot of different parts. It gives you your extreme values, the center of your data, and notice this is, the box represents the interquartile range that I introduced. I don't want to get too caught up on all of these. Oops. Pie charts.
Yeah.
If you've seen a newspaper, you've probably seen pie charts, percentile plots. There's some others. Empirical cumulative distribution function. So basically instead of just having each value, you're adding the values and increasing the values. I don't want to go into those too much at this point, but scatter plots, those are going to be very useful. We can see those in Weka. So you have all your x values. So scatter plots. So you might have your x values along here, your y values vertically. Do I need to label those? And all you're going to do here is literally maybe have a data spot there. You have an x value here, an xy coordinate here, an xy value here. You might have another one here. So this would just be a scatter plot of all your data points. Maybe you have an outlier out here. So this would be an example where it looks like your correlation looks positive, right? Roughly, as x increases, your y roughly increases as well. Everyone seen scatter plots? Contour plots.
Like a map, right?
So people in Colorado, maybe less so in Florida, although the ocean bottom would be an example of it as well. Contour plots, topographic maps. So level curve, is everyone familiar with level curves from calculus? And so you can have a contour plot. Should I draw that? So on a level surface, level surfaces, ocean depth. We could measure ocean depth as well. You might look at some regions. Surface plots, well, now you're actually drawing a surface diagram, say in 3 dimensions, where cutting through, that could be surface plots and contour plots are related. Again, other ways of looking at those, the same data. And vector plots, again, these would be like vector fields from calculus. You've got a, perhaps a, crash that again. So at each point, you've got, say, a vector. And maybe these vectors are different sizes, and they all kind of point to kind of similar behavior. So a plot of directions and magnitudes. The longer the vector, the bigger the magnitude, right? Bigger the velocity or what have you. And finish up. I didn't get nearly probably where I wanted to get, but in essence, you can display additional dimensions in various ways, and we'll probably pick up after this slide on Wednesday. But if you have a scatter plot diagram, for example, you can add additional information. The size of the dot could represent some information. So it could represent, so on a map, city sizes are often represented by the size of the dot. So now you're getting some more information there, right? Small towns, small dots, large towns, bigger dots, big cities, huge regions. The color can give you information, the shape can give you information, and I do want to talk about slicing data and animation on Wednesday. Questions?
Homework due Wednesday, right?
Homework from chapter 1 is due Wednesday. And I will go back.
But you have a... Nope, I wouldn't be very nice.
Oh yeah, you can start rapping or what?
Come on, Jim. This idea wouldn't sound very good.
Questions in Daytona Beach?
We will not see it.
Why do you build me up?
Pardon?
Why did you sit in water?
That was an Eagle Vision.
Terrible. I had to take an asphalt team. Boom.
What did it show up? Were you able to see it?
Normally, the next text box. Yeah. While you were writing, the next one,
It was too small?
if you write, you can see the indicator, right? Like when you type in the text box and then you just leave it, we can't see it.
Oh,
When you
okay.
exit the text, when you exit the text box, we can see it. Yeah.
When I exit, okay. Okay. I get what you're saying now, so I'll make a point of that next time. Was that useful using the whiteboard?
What you say?
Was it useful using the whiteboard to expand on different points?
I think if you write on the whiteboard, that's the best. We see very clear. You can write on your PowerPoint. You can use the Eagle Vision and to write on the white box in the slides, that will be nice.
Oh, okay.
Or write outdoors. Yes, but if there was something you wrote down, we could not see it.
Right, I'll keep that in mind next time.
Okay. Now it's this such, but to measure the food and everything is very difficult for you to know what is that usually measure. What is there and what is measure. So we have people that some projector and similarity, and it depends on what's the data, what kind of distribution it is. Sometimes you do that, for example, in measurement processing, the most frequently used is cosine. You don't normalize anything. It's just all about the frequency, each word is here. And there are some things like a jet physics, or it makes sense. Unless you understand the data, you can learn from something like symmetry. Most